Hi, thanks for staying for my talk. Before I start to talk and introduce myself, I'd like to tell you quickly how lucky I am to literally be here today. Moment. So me and two of my friends decided that we want to go to the Pragma conference, which takes place in Verona, Italy. And for those of you that don't know, it's like 500 kilometers from Warsaw. And we decided to go there by car, which has 15 years. So we stayed for a couple of days, visited the city, and decided that we want to go back on Saturday. I know it sounds pretty unspecial so far. So it's Saturday, 9 a.m. We're driving towards Venice to come back to Warsaw, and then this happens. Yeah, we must have catched on some hole on the road, and our silencer fell off. And we attached it back using some shoelaces, and thought what to do next. As I bought insurance before I went to Verona, I thought, hey, let's call them and ask them for an assistance. And so I called the insurance, and the lady says that you're in Italy, and it's Saturday, and it's siesta, and nobody will come to you. You will have to find a repair shop yourself. So we then thought, okay, let's take it to the nearest open repair shop. We found one. We drove slowly, found someone who speaks English, and presented the problem. Giovanni, the car mechanic, said we had to wait 5 hours because they have lots of cars in the line. So we went to a nearby shopping mall, sat in the food court, waited five hours, and we came back after those 5 hours to find our car fixed, jumped into it, celebrated that everything is okay, and drove away. So we hit the road, and then this happens. We've got a flat tire. We thought, hey, let's quickly run to the repair shop so they can help us. No, the shop has been closed for 15 minutes. We had no choice. We manually replaced with an emergency wheel and searched the map for a nearby for a nearest repair shop which is open 24 hours. And then I thought that I think we ran out of misfortune, that no worse can happen. And we found some nearby repair shop, turned the engine on, then tried to move and realized that the emergency wheel, it's flat, so you don't, the emergency wheel got flat as well. So at that point we had no other choice than to go back to this nasty parking under the shopping mall and spend a night in the car, and it was yesterday. So we did just that, and then the Sunday morning we went to Giovanni once again, and Giovanni showed us the burn marks on the old tire and said it's too dangerous to drive, so we paid a small fortune for the pack of four new wheels. And so just before we hit the road for the 4th time, Giovanni comes to us and for a goodbye says, Fiat no good, go to Deutschland, buy new machine. So, yeah. This is the moral of the story. Never drive 1,500 kilometers with 15-year-old Fiat that barely sticks together. Okay, so my name is Adrian. I work as a senior iOS developer at NetGuru. And today I will talk to you about wrapping C libraries in Swift. This is the agenda. First we talk about setting up the project, then how to add the dependency of your C library, which can be a third-party library or your own library. And then I will talk to you about decorating headers using API nodes. I will tell you what it is. And decorating header using Clang or Clang, I don't know how it's pronounced, attributes. And at the end, I will talk quickly about writing a custom wrapper. This topic, writing a custom wrapper, deserves its own big talk, so I don't dive deeply into it. So without further ado, let's start with setting up the project. So this step is different for Apple platforms and Linux. So for Apple platforms, it looks like this. You create a new Xcode project and add an Objective-C framework target, and please with tests. I know developers may think that if they do not write their own code, they just wrap the library, they don't have to write tests. But in our case, we are actually creating a translation of C APIs to Swift. So we need some kind of proof that it works, even if these are just API calls that do not compile if everything's wrong. So the tests can help us. So yeah, these are the two steps to set up the project actually in for macOS, iOS, tvOS, and watchOS. For Linux, yeah. For Linux, you need to create like the sources directory so that the Swift package manager can build your app or your library, and you can use the IDE of your choice. That's why I wrote the shrug face, because it's different for every person. Okay, so this step was easy, the setting up the project. Now let's move to a more complicated one, which is adding the dependency. So first thing we need to do is to pull the dependency from like GitHub or your own local repository. And to do that, we have three options. Actually, there are four. There are also Git submodules, but I will talk about Git submodules later. And you might think, where's CocoaPods? So, well, unless the C library has a pod spec, the CocoaPod is not very useful because it doesn't build C libraries just out of the box. It doesn't know how to do it. It doesn't know where the sources live. So we have three choices here. We can use a pre-built library if this library of our choice provides us such a thing. We can use Swift Package Manager, of course, but it has a limitation that it cannot be used to create dynamic frameworks, so it cannot be used with iOS and tvOS. We can also use Carthage, which doesn't work on Linux, on the other hand. Okay, so let's start with a pre-built static library. So some libraries provide pre-built binaries to download and use in projects. They usually have an .a archive and a bunch of .h header files. And if your library is one of them, why not take advantage of it? So the only caveat is that this library can only be linked statically because it's an .a archive, but we can link it against our framework, which is dynamic, and everything works together because the exported product is dynamic framework at the end. So these are the steps to create, to use a pre-built static library. We have to download the first, of course, then link the framework with this static library, which is done in the Xcode link binary with libraries phase. And we have to add each of the H files to the Xcode and make sure they are marked as public, so it's visible outside of the module. And this has its advantages and disadvantages. So advantages is that you don't need to build C library from source, which can have like system library. It can depend on the system libraries. It can have like different flags. It has a custom make file, and you have to integrate this into Xcode, and it's painful. And if you use a pre-built library, it's already built, so you don't have to do it. You just drag and drop the header files. But the disadvantage is that you have no version control over it. So each time, for example, if you wrap a libgit into a Swift framework, each time there is a new libgit version, you have to like download it and include it in your repository. And unless the actual libgit has its pre-built dependency in the repository, then you can use, for example, Carthage. So yeah, that's the pre-built static library. Next is Swift Package Manager. So this is the second option to use, and as it's powered by LLVM, the documentation says that SPM can build C dependencies if they contain an umbrella header inside the include folder. And it also produces static libraries. So it's not useful in iOS or tvOS, but you can do the little trick that I presented in the previous slide, that to link the framework with the pre-built library by Swift Package Manager. Yeah. So The steps look like this. We add the dependency to package.swift. I didn't show how to do it, but I think you can read it in README. And then run Swift build, which fetches the dependency from the local or remote Git repository, finds the sources directory, and builds the dependency. One little thing here: if, for example, if something breaks here because Swift doesn't find all the source files or doesn't build the framework successfully, you can use a custom module map file, which I will be talking about in a later slide. So, as always, this has some disadvantages and advantages. So, one of the advantages is it's truly cross-platform and supported by Apple and Woo. It takes care of compiling and linking itself, so you don't have to manually include it in Xcode project yourself. But it doesn't have those iOS, tvOS, and watchOS support, and it doesn't build the C dependencies, which itself have dependencies but do not have a package.swift file. So it's like CocoaPods. It doesn't know if the library of your choice has dependencies. So there is one last thing, one last package manager that I think it can be used here. It's Carthage. So with Carthage we have two scenarios. Some of the C libraries that I saw on GitHub contain an Xcode project file because they are built on a Mac with Xcode. So if this library contains Xcode project, then Carthage actually takes care of everything because it finds the framework target if this scheme contains the framework target. If it doesn't or doesn't include an Xcode project, it just resolves the version and fetches the source code as if it was a Git submodule. The only difference with Git submodule here is that Carthage actually uses version pinning, so you don't have to specify an exact commit as if with Git submodules. So it's actually a little bit better, but under the hood it works exactly like Git submodules. So here are basically the steps to include the dependency using Carthage. You add the dependency, you run Carthage update or bootstrap, and if there is no Xcode project, you need to manually add the sources from the checkouts folder to your target and make sure the header files are public as well. And then you have to build the library from the source. So yeah, this is a very big disadvantage of Carthage, that it requires to build the C library from source because it can be tricky and it has no Linux support. But if there should be a little asterisk, not TM, but with it just works. So it just works if the C library is configured properly. So it does require some action from the maintainer of the C library, or you if you are the author of the library. It doesn't require special files, and there is a little asterisk here as well, because it doesn't require special files if the library has no dependencies itself. So if you use Carthage or any other dependency manager to pull your dependency, you might want to add a custom module map to your project. So a module map contains descriptions of where the library headers are and what are its submodules and what does it export outside. So basically, you include the file in the framework target. It needs to be named exactly module.modulemap, and Xcode places it in the .framework binary package. So it looks like this. I don't think if you can see it. It actually is a simple description of a module, and when included in the custom library, it just says it just points to an umbrella header, and export.asterisk means that all the submodules are exported. And if your framework if the C library doesn't have submodules, it's okay as well. The submodules, for example, can be in the C++ standard library, all of the submodules include the vector, the string, etc., etc. These are all different submodules, and you can import it using import something dot something, and it means it's a submodule. And if you are compiling the framework target yourself, you can include this little piece of code in the module.modulemap file. And if, for example, you are using a system framework, you can actually tell the module that it's a system framework, so it doesn't look in the run path, search path, but it looks in the system files to find the header file. Actually, with this example, it's common crypto, it has one header, so we specify a path for it and include such a module map file, not inside your framework, but inside an Xcode project that imports that framework. I actually named it with the C prefix, and it doesn't require you to do so. I just named it because so that we can see that the library import is actually C library. Okay, so that's all in terms of adding the dependency, and then we will go to the fun stuff, which is decorating the API. So now that our dependency is linked and set up and built, it's time to create an actual wrapper for the library. And first option is to use something that Apple calls API nodes. And API nodes is just a YAML file which are divided by category, and the categories include functions, globals, enumerators, and etc. And it actually specifies a mapping from Swift name to the symbol name that compiler has to emit. So this is actually literally says to the Swift compiler, if the Swift compiler sees foo.init with bar, it has to emit this xyz foo create instead. So it doesn't require you to write any code, it's just create this YAML file and compile it with a long Xcode command that you can find. I didn't paste it here because you won't remember it anyway. This command is available is in the Swift README in the section of building. So API nodes are just the plain YAML files. They contain these mappings of symbols, and it's included in the framework. And for this, with the systems framework, it actually lives in the system directory. It doesn't come with UIKit.framework. And it's used extensively by Apple when Swiftifying APIs for the SDK. For example, when Core Graphics in Swift 3 got all those new objective interface, these are all actually, they live in the API nodes file. So I took a little peek in it. So you can find here different things. The convention of the Swift name is actually the same as with when using CLang attributes, which I will talk about later. And the API nodes have this very big disadvantage that they are not yet documented. These are not private APIs. These are part of the Swift open source project. But when you go to the API nodes and look to the documentation, it says TBD. So it hasn't been done yet. And actually, when I looked on Stack Overflow, when I tried to find information about maybe there is some unofficial documentation, I found a comment from an Apple engineer under an answer that tried to guess how the API nodes work under the hood, that these are subject to change. The whole functionality is subject to change, and this is why they have not documented it yet. So it's fun to know that the option exists, but I would not recommend it to use it in any production code. So the advantage is that you don't need to edit the header files, and you don't need to interfere with the underlying C library in any way. The disadvantages are that it's error prone, it's easy to forget about some symbols, and especially it's hard to maintain when the library changes, because one little change in the symbol name and everything will fail to compile. So I would not recommend it. The more safe solution and the preferred alternative is to decorate the library using clang attributes, which look like this. When the foundation framework is present, it's like a little macro ns Swift name, and if not, then we have to expand it to _ attribute Swift name. Basically, this is widely used in the SDKs and third-party frameworks, and they decorate the types much like nullability attributes. Here are some examples of NS Swift names with the C external functions. So with the NS Swift name, we can emit any like method and variable and read-only method and read-only variable in Swift that we like. So, for example, when we have an initializer-like function which is called xyz foo create, we can actually map this to .init with bar. We can also create variables which are divided by setter and getter, and we have to specify the getter and setter as the prefix before the method. And if the method takes if the C function takes like an instance on which it operates, like in this case, it takes a foo on which it gets bar. It's like a CG context, something that takes a CG context. The first argument is always called self. It's like it's very much like carrying in Swift. When you type CG context dot and type of the instance method, it actually first takes self and then takes the arguments, and it's very much like this. The setter also looks very similar to how you would imagine it is implemented in Swift, that it first takes self and then this new value, which is present in the setters in Swift. And you can actually wrap any function which you like. And also you can write global variables, map global variables with xyz. For example, foo.default bar, which will be a static variable on xyz foo. So C-lang attributes, they are well maintainable because they are coupled with the source code, and if the source changes, then you have it's a good opportunity to change your mapping as well. And and also it plays well with nullability annotations. So if you are actually editing the header file, why not annotate with nullability annotations, so that Swift doesn't see the implicitly unwrapped optionals everywhere. The C-lang attributes are actually documented and widely adopted, and the disadvantage is that you need to edit the original header files, which can, I don't know if it can break the license, for example. It depends on the library. Okay, so now very, very quickly about writing a custom map wrapper. I will actually not talk about it very deeply. I will just mention it. So I will start with the advantages and disadvantages. So the very, very big advantage is that writing a custom wrapper will reduce the friction when interacting with C APIs. It will make the user not see those unsafe mutable pointers, those unsafe functions when operating with pointers, for example. And these custom wrappers can use actually all powerful features of Swift. So, for example, generics, the functional part of Swift. And I would actually, if you have time, if you want to wrap a system library or an existing library like libgit, for example, I would recommend you to write a custom wrapper if you have time. It will not only be easier for you to work with later, but it also will teach you how the underlying C library works, and it will be a great API to use. And the disadvantage is that it's harder to maintain or breaking changes occur. So if you write a custom wrapper, it's like wrapping a system type like an SURL session or common crypto, if something would change, I know it doesn't change very quickly, but if something changes, then the abstraction on top falls apart, and it's harder to maintain this than change a couple of lines in the YAML file or a couple of CLang attributes. So the architecture of the Swift wrapper actually depends on the underlying library, so there is no universal way to make a wrapper library. It's a very broad topic. I think it deserves its own talk. And I would actually recommend you to watch on YouTube the recorded session of Swift and C interop by Chris Eidhoff on Mobile Warsaw edition number 1. It was, I think, the only edition. edition. And watch the Swift API design guidelines session at WWDC 16. They talked about creating those CLang attributes on the C libraries. And I think that's it. So if you have any questions, I'll answer them happily.
Jakie biblioteki były tam używane w obecnej części C?
Proszę?
Kryptograficzna biblioteka, tak? Jeszcze jakieś.
Ale...
Jak używacie najczęściej bibliotek C?
Aha, no akurat kryptograficznych nie. Tworzyliśmy wrapera do CF Stream. To jest typ, który nie ma odpowiednika w Foundation i potrzebowaliśmy to do WebSocketów. Generalnie do Common Crypto już używaliśmy istniejących rozwiązań. No, więc...
No właśnie, bo jakbyście użyli tej biblioteki C, co tam była w przykładzie, to potem nie można wysłać aplikacji, nie? Bo nie mogą używać.
Nie, ona jest akurat systemowa. Jeżeli chodzi o załączanie, po polsku mogę gadać, czy po angielsku? Jeżeli chodzi o dołączanie bibliotek C, to jest dokładnie na tej zasadzie, co Apple sugeruje, żeby dołączyć OpenSSL-a zawsze samemu, a nie linkować do systemowego. I to nie jest, Apple nie powinien odrzucać za to, bo to jest po prostu biblioteka, która jest w innym języku niż C. Jak są gry na przykład, one są w C++ napisane, tylko mają leciutką nakładkę Objective-C. Więc czy to odpowiada na pytanie? W sensie...
Nie, bo jak się robi submisję, to tam jest takie pytanie, czy się modyfikowało biblioteki.
Aha, no to nie jest modyfikacja, to jest właśnie, ten plik module map się zawiera w projekcie, który importuje już Common Crypto. On nie modyfikuje żadnego kodu tam.